Hello physicists. Today we're going to discuss currents and magnetism. And the short and simple idea that I hope to get across today is that magnets pull on currents and currents cause magnets. So, to get there, we're going to first review our rule for magnetic forces that we introduced last time. We're going to extend that to apply to currents, because currents contain moving charges. They are also going to experience a magnetic force. And last time I told you that in the next video we would discuss how to make a magnetic field. Of course, you might say, that's a stupid question, just buy a magnet. Okay, but I'm talking about, from a fundamental level, what is making those magnetic fields. And our answer is going to be ultimately currents. So moving charges cause magnetic fields. Okay, so last time we talked about the Lorentz force equation. The Lorentz force equation is just an equation that says the total electromagnetic force on a particle is the sum of the electric force and the magnetic force on that particle. Now, the tricky thing is that this E, the force from the electric field, and the force from B, the magnetic field, don't necessarily have to be in the same direction. And what makes it even more complicated is that the direction of the magnetic force depends on the orientation of the velocity of the particle moving through the magnetic field. So this V cross B, we learned that if you want to figure out what direction the force is, the magnetic force, you have to use your index finger for the V, your middle finger for the magnetic field for B, so V, B, and then your thumb is the F. All right, and these forces then add like vectors. So you have to add up the x component, y component, z component. And just like with our electric field, if that Q is negative, so if we have a negative electric charge like an electron, for instance, then we would go opposite the direction of V cross B. But that's the same as we had with electric fields, because if we had a negative charge, the force would be opposite the direction of the electric field. Now, a point that I didn't make very explicit last time, but for those of you who have already done this week's lab, it perhaps has crossed your mind. Usually when you learn about magnets as a kid, you talk about the North and South Pole. Of course, that language comes from the Earth having an intrinsic magnetic field, and the compass will align with it. But the way that we usually put this is that we have the magnetic field, the B, is a vector, and it's pointing from the north, out of the North Pole into the South Pole. So what's interesting here is that the magnetic field is actually not pointing parallel to the ground everywhere on the Earth. As you go further north, it's pointed more and more obliquely. But the north-south horseshoe magnet actually does provide quite a good approximation of a constant magnetic field pointing from the north side of the magnet to the south side of the magnet within the gap between the sides of the horseshoe magnet. Now, something that's a little strange about this is that if you cut a magnet, you don't get just the north side and just the south side. You get a new north and south. So that's what this picture is trying to indicate. And we'll talk more about why that is next time, but the short version is there are no magnetic monopoles. That means that you don't have a source of magnetic charge like you did with the electric field. All you can have are little loops of current. So currents are causing magnetic fields. So you don't have something that's just causing that magnetic field in a static sense, the same way that a charge was causing the electric field just hanging out. Okay, so here's a nice visualization of what I just said, where you sprinkle iron filings around a magnet in between the filings. Try to align themselves with the magnetic field to lower their energy, and in between that horseshoe magnet you can see that you get a relatively constant direction for the magnetic field. Now, I want you to focus on this equation and try to make sure we understand it. Okay, forget about the electric field part for a second. We're just looking at this QV cross B. It says, complete the following sentence. When a positively charged, okay, so Q is plus, particle is released from rest in a region that has a magnetic field directed due east. So there's your B. Here's your never eat shredded wheat, north, south, east, west. And it says, the particle will. Okay, so we're releasing it from rest, and we want to know something about its acceleration. Well, this is sort of an F equals ma problem, and the force here is going to be this QV cross B. But if our V is 0, that means that our force from that the magnetic field is also 0. So if I put a 0 in there, no force. If I put a 0 in there, so if I have like a neutron that doesn't experience electric charge, then you're not going to get much action from the magnetic field. If you put in a stationary charge, you're not going to get much action from the magnetic field. So you have to have two different things. You've got to have, well, I guess three different things. You have to have charged, so it's got to be, to experience magnetic force, your particle has to have an electric charge. It has to be moving, and the magnetic field and the direction of the magnetic field and the magnetic direction of the movement can't be in the same direction. Okay, so this is the cross product part of it. Remember, V cross B, these are vectors. But if you want to find the magnitude of that, it's going to be the magnitude of V times the magnitude of B times the sine of the angle between the two. Okay, so if that sine is 0, remember, sine looks like this. There's 0, 180, or so, whoops. Yeah, no, I'm okay. 360. So at the angle of 0, this is also going to be 0. Oh, okay. So the particle will remain at rest. All right, so let's think a little bit more. This problem is one of your homework problems, but we're going to do most of it right now just to make sure we are comfortable using our right-hand rule. Remember, V cross B gives you F. So our force equals, our force from the magnetic field depends on V cross B. Now, what may not be immediately obvious to you here, but which is true, V and B from this equation are not required to be perpendicular or parallel or anything. They can be whatever they want. The magnetic force, though, because of this equation, has to be perpendicular to V and perpendicular to B. So that's what this right-hand rule is trying to get at. These two, they could be perpendicular. That's how you get the biggest force, but the F is required to be perpendicular both to either one of these. So if these are close to parallel but not quite parallel, you can still get a force that's not very big. So let's just take a look at two different examples here. It says figure 28.22 shows three situations in which a positively charged particle moves at a velocity through the uniform magnetic field and experiences a magnetic force. In each situation, determine whether the orientations of the vectors are physically reasonable. Okay, so we have a positively charged particle, so we don't have to worry about this. No funny business. We don't have to reverse any of the signs. Now we're going to be just working with our V cross B equals F. Now I think I introduced this notation last time very briefly, but let's just remind ourselves that dot and X notation comes from the idea that we're pretending our field is something like an arrow, and our arrow has some feathers on the back of it. And if the arrow is coming out of the screen, you see the point of the arrow first, so this is out of screen. And if the arrow is going into the screen, then you see the tail, the tail feathers. So there's the X. Okay, so that's what this notation is trying to get at. Coming out, going in. So let's take a look. Physically reasonable. So if I have V cross B gives me F. Now, I want you to try to say, I'm going to sort of step on this one because I'm going to say this is not reasonable. Why not? Well, that force, magnetic force, has to be perpendicular both to V and to B. Okay, so is the magnetic force perpendicular to B? It turns out it actually is, because B is pointing into the page, the magnetic force is pointing in the page, so those are perpendicular. But the magnetic force is not perpendicular to V. Okay? Why? So FB not to V. So it's not, FB is not perpendicular to V. Okay, now let's look at this next one. V cross B. V is my index finger, B is my middle finger, F is my thumb. V cross B is F. Now this F is out, so this is out of the page. And this works exactly as I would expect. Since V is in the page, this is pointing directly out of the page. V and FB are perpendicular. B and FB are also perpendicular. And so this works. Okay, so I've done those two. I'm going to leave this last one to you. All you have to do is use your right hand rule and see if it could be right. Here's another homework problem. Last time we discussed electrons going around in or electrons or protons, charged particles moving around in a constant magnetic field. Now take a look at this. It says, in figure 2836, a particle moves along a circle in a region of uniform magnetic field with a B of 4 milliteslas. The particle is either a proton or an electron. You must decide which. It experiences a magnetic force of magnitude 3.2 times 10 to the minus 15th. Okay, so FB equals 3.2 times 10 to the minus 15th newtons. What are the particle's speed? What is the radius of the circle? And what is the period of motion? All right, so I want to help you set this problem up. You may not get to the end of it, but it may be useful to get there. So the first part says, what is it a proton or an electron? And so that's going to be important because depending on which one it is, you're going to look up a different mass that's going to go into this. The charge is going to be the same. That's just going to be your fundamental charge, E, 1.602 times 10 to the minus 19th coulombs. Okay, but let's take a look. Now, in this picture, I know the direction of B, I know the direction of V, and I actually also know the direction of F. Why do I know that? Because moving in a circle means that it has a centripetal force, that force that's towards the middle of the circle. So there's my FB, which I can draw in. So if I had a positively charged particle, it would follow the right-hand rule. So let me try that. I'm going to go V cross B. V cross B would give me F. So if this were a positively charged particle, try it with your own hand. V cross B gives you F. We would expect the force to be pointing that way. But the force is in fact pointing the other way. V cross B is pointing this way rather than with my thumb. So this must be a negative charge. Okay, and because it's a negative charge, we can tell in this problem that we are going to be looking at an electron. Now, because we have an electron, we can go ahead and start to work out our different solutions for this problem. Now, you'll remember force is Q times V cross B. We know FB. We know Q because it's going to be just that 1.602 times 10 to the minus 19th coulombs. That's our elementary charge. We don't know V, and we do know B. So B is 4 millitesla, so 4.00 times 10 to the minus 3 Tesla. So using F equals Q times V times B, you're going to be able to find V. F equals E V B. You're going to go ahead and solve for V because that's the speed. The speed, of course, is going to have units of meters per second. Then, once you have that, you'll know V. You can look up the mass of the electron. We know this Q is going to be 1.602 times 10 to the minus 19th coulombs. You've already been given the B. So, using the formula that we derived last time from Newton's second law and centripetal acceleration, you are going to be able to find R. Okay? So you're just going to use that mv over qb equation that we described last time. Now, for the third part, it asks for the period of the motion. Period of the motion. So that is asking us how much time does it take for that electron to go around the, I should go around the other way, go around the circle once. Well, if I have v equals 2 pi r, that's the distance around the circle over the time it takes to go around the circle, you should be able to find that t, that period. So that's a time in seconds because velocity is distance over time. So this is, I guess I should say speed, because the velocity is constantly changing and always pointing tangent to the circle. It's always changing direction. All right, so I think that's enough for you to do that problem the rest of the way. Now, there's a ton of interesting experimental consequences of the magnetic force. Now, one of them is that finally we can tell which type of charges move. So you might I remember that I have this opinion shared by, I would say, virtually every physicist, that it's sort of annoying and weird that we have current going this way means that electrons with a negative charge are going the other way. But that convention really couldn't have been known at the time when it was made up. Ben Franklin was the one who came up with this idea of positive and negative fluids that are, can be separated. But which one of those was causing the currents was not known until quite a bit more development. Cathode rays and that sort of thing in the 1880s and 90s. Now, one way that you can tell what sign your charge carriers have is the following. So let's say that you have a wire or a plate of material, and you put it inside of a magnetic field. So in this way, you notice they put the crossed feathers so the magnetic field is pointing in to the board. Now, if you have this current, this will the magnetic forces will cause there to be a charge buildup from one side of the plate to the other side of the plate. So what traditionally is done is they put an extra battery onto the plate, and that extra battery provides a voltage, and that voltage is effectively making an electric field. Okay, so there's our direction of our electric field from our battery, and you can turn up that. So at the beginning, when you're doing this, your charges are building up on the side of this plate, and you want to tune it such that instead of having charges build up, instead they're going straight through. All right. So what you do is you crank up your voltage until you get the magnetic force and the electric force basically balancing out, and the current just goes through nicely. But essentially what this allows us to do is figuring out whether we have plus charges moving down in this picture or minus charges moving up. And so this is called the Hall effect. The Hall effect is that if you put a current through a wire, or rather a slab, and you put it in a magnetic field, you will see there be some voltage across these plates. And that voltage, whether it's the electric field is pointing to the left or to the right, can tell you whether your charge carriers are either negatively charged or positively charged. Now, if we do it in a normal metal like we would be thinking about in this class, or in fact in a lot of the ceramics that you would use as a resistor, you will find that the charge carriers are negative, just like we've advertised. There are interesting cases, however, where the charge carriers are positive, and that understanding that effect requires you to think in terms of the electrons not being just little classical billiard balls, but instead being a sea of little waves. And they follow what's called the Pauli exclusion principle. And effectively, all of those electrons moving in tandem allow it to appear like a positive charge is moving instead of a negative charge. Okay, so it's a little complicated, but this idea is called a quasi-particle, where the collective motion of many particles causes the appearance of a particle. All right, had to stop the video for a moment so I could talk to Vanessa from Dealer Service Center. Okay, so that's the Hall effect, and this is exactly the sort of problem that this example I worked out at the end of the last video is trying to get at. So if you are interested in this problem, the effective idea is that by having an electric field that's pointing this way and a magnetic field that's pointing cross, so in or out of the page, you're going to be able to balance the forces such that the total force on the particle is 0. Okay, so if you want to see that, I did that on at the very end of the last video. Now, another interesting application, we've talked about how if you just have a constant magnetic field, you can get a particle to rotate. It goes around in a circle, round and around and around at a constant speed. But the physicists in the first half of the 20th century were very excited that they could start to manipulate charged particles, and they wanted to get them going faster and faster and faster so they could smash them into things to understand their microscopic constituents a little bit better. And so this is a clever little machine called a cyclotron. They started very small, and then if you see modern cyclotrons, there are some that are the size of a room or even bigger. And the idea here is that in between these plates, there's an oscillating electric field such that every time the electron goes across this plate, it gets a little kick. And then it gets a kick the other way when it goes around, and it's getting a kick, kick, kick. And so it's getting a little bit faster every time it goes around. So the reason that it's spiraling outward is that it's getting faster and faster and faster and faster and faster and faster and faster. But the remarkable thing is that you can tune this, and the frequency with which the object is going around is not changing. So it's going around, its speed is picking up, but the radius is getting bigger as it gets faster, so the rate at which it's going around is approximately constant. Okay, so that's how you can use this oscillator to tune this. It's called the cyclotron frequency. If you're interested in that, I recommend looking up cyclotrons. It's actually not too hard of a derivation, but we don't need it right now. And these fast particles are in fact used for all sorts of things. When I was undergraduate myself, I went and did a research experience at the Cyclotron Institute at the University of Indiana, where they have converted their old cyclotron, which used to be for research, into a medical facility where people get their brain tumors irradiated by fast protons. So there are all sorts of interesting applications of this. Now, we've already talked about how magnetic forces can pull on charges that are moving. But now I ask you to get a little philosophical with me. What is a current but a charge that is moving? So this moving charge is a current. And if we think about this, look at this. This is newtons equals coulombs times meters per second times Tesla, right? But if you look at it, this coulombs over seconds, that is basically a current. And if you add up all of those coulombs per second, all of those different currents, if you add them up, you can talk about a total current. And this meters then is the total length over which that current is being applied. All right, so you can think about this, and this of course is still just B. So this force then is the current times L still has a direction. We consider L to be in the direction of the current that's flowing. B still has a direction. So our force still has a direction. And if we put our current in exactly the same direction as the magnetic field, it still will experience no net magnetic force. But we can use this now to talk about how much force is going to act on a current that's running through a magnetic field. So here's a nice little homework problem. It says a horizontal power line carries a current of 5,000 amps. Okay, pretty ambitious. From south to north. So there's our I. There's our north, south, east, west. Earth's magnetic field is directed toward the north and inclined downward at 70 degrees to the horizontal. Okay, so this must be in a case if you think about up north. If you're close enough to the North Pole, the magnetic field is pointing in towards that thing. So if we're looking at this from the side now, here is our I, and there is our B. So 70 degrees to the horizontal. So it's pointing basically into the page down like that. Then it asks us, what is the magnitude and direction of that magnetic force on 100 meters of the line due to the Earth's magnetic field? So our force is going to be I, sorry, let me put it, yeah, no, this is okay, I, L cross B. So if I want to go ahead and find the magnitude of that, I'm going to put in the magnitude of I. So that's going to be my 5,000 amps. My L, it gives me as 100 meters. And then my B is 60 microtesla. So you're going to have to put that in terms of just teslas, 60 times 10 to the minus 6 Tesla. So it's going to be ILB, and then because this is a cross product and it's at an angle, you're going to have to use the sine of that angle. Okay, so our angle in this case would be that 70 degrees. So make sure that you have your calculator in degrees when you stick these numbers in. So that'll give you a magnitude. Now let's think about what direction would this be. Well, you've got to get your fingers out. You're going to go I cross B gives you F. So in this case, if you're going north and then your B finger is going slightly into the page, then your thumb, so this is our direction of B, our thumb is going to be going over here. So this is the direction of our force. So our force is actually going to be pointing west. Another way to look at this is north, this is slightly downward, and then the force is going to be going into the page. Now another example of this, I'm going to let you work this out yourself, but the idea is what if you have a bar that is in the magnetic field? The force of gravity is going to be pulling the bar down. They give you the 13-gram wire, so you're going to be able to say the force of gravity is equal to m times g. M, you'll have to put in 13 grams in kilograms, so 0.013 kilograms. So you already can, from that, know what the force of gravity is, and they tell you it's suspended by a pair of flexible leads in a uniform magnetic field of magnitude 0.440 Tesla. Then it asks what are the magnitude and direction of the current required to remove the tension in the supporting leads. So what your job is then is to say if the tension is removed, that's effectively saying that there's not any force that's pulling the wire down anymore. So that means that the gravitational force will be balanced by a magnetic force. So you know the direction of the magnetic field, it's into the page. You know the direction of the magnetic force, it's up, and you have to decide what is I, what's the magnitude, and of course so you're going to have to solve for that using the FB is going to equal FG, so you know the size of the magnitude of that force. You know that the magnitude of that force is going to be related to I times the length of the wire times B, and you're going to find the direction. So you're going to you're going to use that equation to find the magnitude of the current. And then you're going to have to find the direction of your current by using your right-hand rule. Okay? So F is up, B is into the page, and then you're going to use your right-hand rule to try to figure out which direction, left or right, that your current is flowing. Now, this type of problem might seem a little esoteric. What's the point? Why do I need to know this? But it turns out that almost all of our important electric motor applications are essentially magnetic in nature. And so these magnetic forces are what allow us to get loops that turn, essentially. Now, most motors are not DC motors. Most motors are actually a little more complicated. If you're using an alternating current electric motor, a lot of them are based off this contactless model introduced by Tesla back in the early 20th century. And but the DC motor is still used in some places, and it's sort of easy to understand, because what it requires is that you have this permanent magnet and the current that's running through it. Why do you have a current? Well, you have a battery. The V cross B, so essentially the I cross B leads to an F. So in this picture you have, for instance, I going in this direction. There's your I. I cross B gives you a force that's pushing down on one side, and I cross B gives you a force that's pushing up on the other side of the loop. So it's pushing down on one side of the loop, up on the other side of the loop. Essentially what this creates is a torque, and that torque causes the wheel to spin. And essentially all of your electromagnetic applications, from your power plant that has a whirling turbine to everything else, is tied up with this magnetic spinning loops in magnetic fields. So here's a very nice animation from this German fellow's personal website. I've put a link to this in your class notes. But I encourage you to take a look at this, because essentially what's happening is that you have this device called a commutator, which is tricking the circuit into always giving the current in the correct direction so as to produce a torque. And you notice the way that it works is that there's a contact between the leads, and this is a battery, and there's a portion of this where you have a break in the circuit. And at that point, the momentum of this, the angular momentum of the wheel continues it flowing. The force lets off for a second while the direction of the current effectively changes direction, and it allows that torque to be directed in the same way over and over and over, and gets your engine spinning. So I don't think me saying it is going to be as effective as you taking a look at this website and trying to convince yourself that this would in fact work. Now, the last thing I want to just tease today, okay, so that's our important application, is a DC electric motor. We've already said that currents get pulled on by magnetic fields. But where we're going with this is that currents can also cause magnetic fields. Now, you'll remember this is sort of where we started, is Ørsted setting up this voltaic pile and noticing that a compass gets deflected around a current. So by using a compass and iron filings, they were able, even in those early days, to map the magnetic field outside a line of current. And I want you to get excited. It turns out we've got another right-hand rule. So this other right-hand rule says, if your thumb is pointing in the direction of the current, then your fingers are going to curl around the wire in the direction that the magnetic field is making loops. Okay, so the magnetic field is making loops around here. In this picture, for instance, the magnetic field would be pointing this direction over here. It would be pointing this direction over there. It would be pointing this direction over here, and behind the wire, it would be pointing like this. Now, how can you know that? Whoops, did I get the direction on that wrong? Yeah, whoops. All right, sorry. This is why I need to actually get my hand out and do it while I'm not writing. Okay, so if my current is going like this, there's my current going up like this, then my magnetic field would be going like this, like this, like this, and like this. So at each point around here, it has a particular direction, and the way that you can figure out what that direction is by hooking your fingers around like this. Thumb is in the direction of the current, fingers are pointing in the direction of the magnetic field. Now, to get us started on this, we're going to just think about the magnetic field of a long line of current. The magnetic field of a long line of current has this form. It depends on a new constant of nature. Okay, this is you remember we had epsilon naught when we were talking about electric fields. Here we're going to have this number called mu naught. Epsilon naught we called the permittivity of free space. Mu naught is sometimes called the permeability of free space. And if you have a very long wire, the magnetic field dies off as you go out, just the same way that the electric field died off as we went away from a long line of charge. So this is a long line of current. You don't have to have a net charge. You do have to have charges moving, though. And the way that we figure out what our direction of our charge is, in this case, they have an X, so this is a magnetic or a current that's going into the page. Here's our direction of our magnetic field going like this. B, 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 B. And so it says the magnetic field is, for a long time of current, is if it's infinitely long, it has this form. So it's dying off as 1 over R, mu naught times I. So the bigger the current, the bigger the magnetic field. The farther away from the wire is, the smaller the magnetic field. And then we have this curious number that is a measurable constant, which is about 4 pi times 10 to the minus 7th Teslas times meters over amps. Why? It's because you need to get the units to work out on this. Now, as we'll discuss more next time, there's actually a fundamental rule called the Biot-Savart law, which allows you to find the magnetic field from any configuration of static currents. So this is the sort of the fundamental law of or magnetostatics, the same way that Coulomb's law was the fundamental rule of electrostatics. But if you just want to look at a simple example, all right, it says, let's just look at one. The tricky thing, and the thing that's going to cause us a little bit of pain, is that just like we had electric fields add like vectors, magnetic fields can also add like vectors. So just to tease this, let me go through a specific example, and we'll do more of this next time. It says, at a certain location in the Philippines, Earth's magnetic field of 38 microteslas is horizontal and directed due north. Never eat sour watermelon. Okay, so there's our B from the Earth. And it's equal to 38 times 10 to the minus 6 Tesla. Suppose the net field is 0, exactly 1 centimeter above a long straight horizontal wire that carries a constant current. What are the magnitude and direction of the current? Well, if right at this position the total magnetic field is 0, that must mean that the magnetic field from the wire is exactly opposite that of the Earth. So the magnitude of that B wire is equal to the magnitude of B of the Earth. Okay? And if we want to find out what direction of current, now imagine that we're below this now. This point is above our wire. If I want to get that B wire that's above me to be pointing down, I would need a current below this plane, the plane of this, that's pointing like this. There's your eye. So just to picture this in another way, let's suppose my eye were going into the page. In that case, if my eye were going into the page, my B wire would be like this, and then my B earth would be going like this. Okay, so the magnetic field of that wire is going in different directions for every point around the wire, but then right above it, it's canceling out. Now, if I am just 1 centimeter away, okay, that means I know my R is 0.01 meters above that current, which is what I want to find. And so what I can do is I can use this equation, B equals mu naught I over 2 pi R, to find the size of that current. I equals 2 pi R times B over mu naught. And if I stick in my numbers, it turns out this works out pretty nicely because I have 2 pi times 10 to the 0.01 is 10 to the minus 2 meters times b, which is 38 times 10 to the minus 6 Tesla. And then if we look back, that constant is 4 pi times 10 to the minus 7th Tesla meters over amps. 4 pi times 10 to the minus 7 Tesla meters over amps. So the Teslas cancels out, meters cancels out. This puts the whole thing to be in amps. Here my 2 pi and 4 pi gives me just a 2 down here. I have 10 to the minus 6, 10 to the minus 7th, so that gives me a 10 to the times 10 to the minus 2, so that gives me a 10 to the minus 1, and then 38 divided by 2 is 19. Okay, so 19 times 10 to the minus 1 gives you this 1.9 amps, and as we determined here, it's flowing east. Okay, so that's the type of problem we're going to be tackling in the next days. Don't get too scared, but realize this is going to be essentially like a lot of problems we did in Unit 1, just with trickier directions. But I don't want you to lose sight of the main message of today. Magnetic fields pull on currents. So we had that last time in the form of electrons being whipped around in circles. Today we can have literal wires being pulled on in one direction or another because of the charges that are moving inside of them. And those pulled currents have many applications, like, for instance, a direct current motor, if you use some tricks. And then finally, we're going to push forward and say, just as currents are pulled on by magnetic fields, currents also are the source. They're what's producing the magnetic fields. Okay, so just like in electric fields, charges were producing electric fields, and charges are getting pulled on by electric fields, currents are producing magnetic fields, and they are pulling on magnetic fields. Okay, so thanks for watching. Please bring some homework problems for Friday.